In the last video, we talked about how large-scale deep learning jobs are generally structured. This video shows you how to implement one of the most important parts of large-scale deep learning jobs, namely sequential I/O. For that, we use the WebDataset library. The WebDataset library implements the PyTorch iterable dataset interface and is fully compatible with PyTorch data loaders and frameworks. For WebDataset, data is stored simply as POSIX tar archives of files. You can create such archives from existing file-based datasets using the tar program or using the tar writer class in the WebDataset library. All I/O in the WebDataset library is sequential, and that yields high performance when reading from rotational disk drives and network connections. The WebDataset library itself can be obtained in source form from GitHub, or it can be directly installed using pip3 install WebDataset. Web datasets can be stored on your local disk, or in web servers, or in object stores, or in the cloud. You refer to a web dataset just by a standard file system path or URL. Now, web datasets usually consist of many shards, and in order to express which shards compose a web dataset, we use brace notation the same way it is found in the command line shell in Linux. So we use brace notation to enumerate all the shards that are part of a web dataset. In the example below, you see a 100 times pre-augmented subset of ImageNet stored in 13 shards. So there is a total of 1,300 files. Now, this dataset is stored on a local web server, 192.168.1.22, in a subdirectory called ImageNet subsets, and the shards are of the form living_9- and then the augmentation number, and then the shard number within that augmentation. So the augmentations are numbered 0 to 99, and then the shards are numbered 0 through 13. But the interpretation of these shards and shard numbers doesn't really matter. As far as web dataset is concerned, this is simply 1,300 files containing image data that we want to use for training. So in order to open these 1,300 files, we just hand the URL to the web dataset constructor, and we get back a dataset object. And this dataset object, as I was saying, is a standard PyTorch dataset or iterable dataset instance. Now, since datasets are just stored as POSIX tar files, we can use standard Unix tools to look at them. So this particular dataset consists of images and corresponding classes. And both the images and the classes are stored in separate files. The files with a common base name correspond to a single sample. So for example, the first file is 0.class, followed by 0.ppm. The 0.class contains the class, and the 0.ppm file contains the corresponding image. The format we use for representing these images here is the ppm format, which is an uncompressed format, and that allows us to skip the JPEG decompression, which can be computationally costly. And since these images are fairly small, the trade-off is a good one for this particular dataset. In other cases, you might actually want to use JPEG compressed or PNG compressed images and store those in the tar archive. As I mentioned before, web dataset instances are just instances of a PyTorch iterable dataset. As such, we can iterate over them. And an iterate over a web dataset just yields samples. Each sample is a dictionary consisting of keys and values. The key is generally the extension of the file that makes up a sample, and the value is the binary content. There's a special dictionary key called __key__, which identifies the sample itself. That is the base name of the files, the common base name that makes up the files of the sample. Images in web datasets are stored just as image files contained in a tar archive. Since Python already knows how to decode many file types, we can simply tell WebDataset to decode known file types automatically. The decode RGB method call here tells WebDataset to decode all images automatically into an RGB tensor. Since most PyTorch augmentation pipelines are built around file inputs, and since WebDataset stores image files, those pipelines can be reused. Usually file-based datasets decode images into PIL format in PyTorch, and we're just telling WebDataset to do the same thing by calling the decode PIL method. WebDataset by default returns dictionaries containing the contents of all the files comprising a sample. But most PyTorch training pipelines expect tuples. The toTuple method tells the WebDataset class which entries in the sample to extract and put into a tuple. After we've converted the WebDataset samples into tuples, we can then apply the standard Torch Vision augmentation functions to perform image augmentation. Here we use the mapTuple method to apply a simple color jitter followed by a conversion to a torch tensor. Finally, we perform a shuffle with a shuffle buffer of size 1000. This also enables shard level shuffling. Here we see the previous data loader pipeline in action. In this loop, we just create 5 separate iterators and then request the first sample from each iterator and display it. These images are representative of shuffled and augmented training samples from this dataset. This slide shows WebDataset being used as a part of a PyTorch Lightning training loop. Notice how little needs to be changed. You simply insert the WebDataset constructor into the train data loader method the same way you would insert any other dataset constructor there. Nothing else changes about training. Finally, here you see training in action. Again, nothing changes about training relative to just loading the data from local disk. But in this case, training is taking place against a 1.3 terabyte dataset stored on another server and accessed through an HTTP connection from a web server.